In class, we learned about some powerful techniques in motion planning, including kinematic trajectory optimization. As we discussed, however, they often tend to avoid collisions too conservatively. In addition, real-world tasks frequently have multiple potential solutions. In this project, we take inspiration from cognitive science models of how humans plan and make decisions and explore how we can obtain robot trajectories that are good, or more precisely near optimal, and that also take varying approaches to traversing the environment. My name is Jovana, and my friend Stewie and I are going to present our project on Markov chain Monte Carlo, in short MCMC, motion planning for Boltzmann rational trajectory optimization. In this project, we implement 5 MCMC algorithms of 0th, 1st, and 2nd order, and combine random sampling and optimization to generate good and diverse trajectories. We evaluate the trajectories and perform ablation studies on 2D navigation and 3D manipulation problems. We show that 0th and 1st order methods prove as sufficient for 2D problems, and that solving 3D manipulation tasks benefits from 2nd order derivatives. Finally, we suggest that our MCMC motion planners may be a helpful way for robots to model humans. Next, we discuss what we learned and our process of getting there. We learned that Markov chain Monte Carlo is quite a powerful method for generating samples from desired distributions. Indeed, even for the simplest of the algorithms that uses no derivative information, we were able to obtain a surprising amount of viable trajectories. We experienced how defining the cost function for the problem can be difficult, and for just a small change in how we penalize obstacle collision compared to the length of trajectory, we observed trajectories going straight through the obstacles and away from the goal. We compared the algorithms with respect to their time complexity and the kind of trajectories they generate, and we found that for 2D environments, unadjusted Langevin algorithm requires least tuning to generate diverse obstacle-avoiding trajectories. We learned that sampling from a Boltzmann distribution, which is commonly used to model human decision-making, allows the trajectories to explore multiple potential solutions. And as would make sense intuitively, we found that the variance of the path scales nicely with the number of obstacles. The beta parameter of the Boltzmann distribution, commonly referred to as the rationality coefficient, intuitively corresponds to how strong is the preference for low-cost trajectories.
Next, we performed experiments on a 3D manipulation environment involving motion planning to a desired pose of a 7-degree of freedom robotic arm. Here we compare 2 trajectories sampled from Newtonian Monte Carlo, a 2nd order method, with beta equals 0.1 and beta equals 10. We can see that for beta equals 0.1, there's quite a bit of shaking and suboptimality, while for beta equals 10, we see a smooth interpolation to the desired final pose. We also compared to Hamiltonian Monte Carlo, a 1st order algorithm that's widely considered as the gold standard for MCMC, with beta equals 10. And we observed that there's quite a bit of wild oscillation. This is consistent with our quantitative results, which show that for this 3D motion planning problem, only the 2nd order algorithms are able to optimize well enough to discover low-cost trajectories. At the same time, Newtonian Monte Carlo also produces the most diverse trajectories, and therefore does the best at generating diverse and near optimal trajectories. In this project, we successfully used MCMC algorithms to produce diverse and approximately optimal trajectories for motion planning problems. We also consider several directions for future work. Most importantly is a more complete evaluation with more diverse and complex experimental environments. Second, in handling constraints, we perform a projection step, which causes us to lose the technical condition of reversibility and theoretical convergence. It would be interesting to see how we could restore these with more advanced methods. Lastly, the direction that we are most excited about is in using our motion planning algorithms for Bayesian trajectory prediction and human-robot collaboration problems. Thank you for listening to our presentation, and we hope you enjoyed learning about what we worked on.